We now have our complete toolkit for factoring. When we're confronted with a polynomial, we want to start by trying the basic techniques, because if they work, they're going to be easiest. The next thing we want to consider is, do we know any irreducible quadratic factors? In real life, this might come from something about how we originally set up the polynomial. It might come from some other source. In math class, often it will be given. If we do have an irreducible quadratic factor, we should divide by that first. Once we've divided by any factors that we already know, then we can use Descartes' rule of signs to analyze the real roots. This is optional, but especially if we have a lot of possibilities or if we have a relatively high degree, narrowing things down is useful. And then once we've narrowed down the possibilities, we try possible rational roots until either we're down to a remaining quadratic factor or until we've eliminated all the possibilities. Once we get down to a quadratic factor, we can use our methods for factoring quadratics. We can use the AC method, or completing the square, or the quadratic formula to find the last two roots if they exist, if that last quadratic factor is not itself irreducible. So let's actually go through that process. Here's a polynomial. We want to find all of its real roots, and we want to factor it fully. And to get us started, we're given that x squared plus 6x plus 13 is a factor. So the first thing we want to do is to divide out our irreducible quadratic factor. So we're going to say x squared plus 6x plus 13. Again, not linear, so we can't use synthetic division. But we'll divide that into x to the fifth plus 0x to the fourth, right? I don't have an x to the fourth term, minus 14x to the third, minus 26x squared, plus 105x, minus 26. And so we'll go through the long division. First, we're going to say x squared into x to the fifth. That goes in x to the third times. X to the third times x squared, that's x to the fifth. X to the third times 6x, that's going to be 6x to the fourth. X to the third times 13, that's going to be 13x to the third. And now we subtract. X to the fifth minus x to the fifth is 0. We have 0 minus 6 is negative 6. So negative 6x to the fourth. Negative 14 minus 13 is negative 27. So negative 27x to the third. And then we'll bring down negative 26x squared. Okay. Now we're going to do x squared into negative 6x to the fourth. That's going to be a negative 6 times x squared. Negative 6x squared times x squared is going to indeed be negative 6x to the fourth. Negative 6x squared times positive 6x, that's going to be negative 36x to the third. Negative 6x squared times positive 13, that's going to be, oh, yuck, a negative 78x squared. Well, we're told that this is a factor, so eventually those unpleasant numbers are going to come out in the wash. So negative 6 minus negative 6 is indeed 0. Negative 27 minus negative 36, that's going to be a positive 9. So we'll have a positive 9x to the third, negative 26 minus negative 78. That's going to be a positive 52. So we'll have plus 52x squared. And finally, we'll bring down this plus 105x. Okay, next term, we're doing x squared into 9x to the third. That's going to be a plus 9x. So 9x times x squared is indeed a 9x to the third. 9x times 6x, that's going to be a 54x squared. 9x times 13x. 9 times 13 is absolutely a job for a calculator. That's 117x. Subtracting, we have 9 minus 9 is 0, of course. 52 minus 54 is negative 2. So we'll have negative 2x squared. And then 105 minus 117 is negative 12. So we'll have negative 12x. Oh, this isn't so bad. We'll bring down our minus 26. And it looks like these numbers are pretty okay. Right, our last round, we're saying x squared goes into negative 2x squared. That's just going to be a negative 2. Then negative 2 times x squared, that's negative 2x squared. Negative 2 times 6x, that's negative 12x. Negative 2 times 13, that's negative 26. And as we hoped, when we subtract, we just get remainder 0. So that's broken down our original polynomial as x squared plus 6x plus 13 times x to the third minus 6x squared plus 9x minus 2. And now we have a second factor that has 4 terms, degree 3. It might occur to us to factor by grouping, but looking at these two terms, I've got a 6 and then a 2. So the constant is smaller than the x squared, but the x cubed is smaller than the x. Grouping isn't going to work for me. So next I want to say, for my remaining polynomial, what are my possible rational roots? And I have good news. My p has to be a factor of negative 2, so plus or minus 1, or plus or minus 2. My q has to be a factor of 1, so just plus or minus 1. My possible rational roots are negative 1, 1, negative 2, 2. So that's not a lot. How do I determine which one I want? Well, trial and error, right? I'll use synthetic division. Looking at this polynomial, Descartes' rule of signs says my original polynomial x to the third minus 6x squared, that's one sign change, plus 9x, that's the second sign change, minus 2, so that's 3 or 1 positive. If I take p of negative x, right, the sign of the x to the third changes, so that's negative x to the third. X squared and negative x squared are the same, so that stays negative 6x squared. The sign of x to the first changes, so that's minus 9x, and then the constant stays the same. No sign changes there, so 0, negative. I'm not going to check -1 or -2 because I know I don't have any negative real roots. So I'll have to try our 1 and 2. I'm just going to copy that polynomial onto the next page. And then we're going to use synthetic division for our trial and error. So I'm going to try 1 first. And my coefficients are 1, -6, 9, and -2. So copy the 1. Then 1 times 1 is 1. -6 plus 1 is -5. -5 times 1 is -5. 9 plus -5 is +4. 4 times 1 is 4. -2 plus 4 is +2, which is not 0, so 1 is not a root. I guess I'll try 2. Again, my coefficients are 1, -6, 9, and -2. So I'll copy the 1. 1 times 2 is 2. -6 plus 2 is -4. 2 times -4 is -8. 9 plus -8 is 1. 2 times 1 is 2. -2 plus 2 is 0. Okay, so I got remainder 0. That means that 2 is a 0 of the polynomial. In other words, x to the third minus 6x squared plus 9x minus 2. That factors as x minus 2 times x squared minus 4x plus 1. And then I don't have any possible rational roots left. It's pretty easy to see looking at this that 2 is not going to be a root, right? Because my constant is 1. So it must be that that polynomial is prime. But I can find zeros of x squared minus 4x plus 1 using our methods for quadratics. I can use the quadratic formula, or I can use completing the square. And because these numbers are quite small, I'm going to choose to use completing the square. You could do this using the quadratic formula if you prefer. Right, so I've got x squared minus 4x plus 1 equals 0. I'll subtract 1 on both sides. X squared minus 4x is -1. And then to actually complete my square, I have my x squared. Splitting -4x in half, I'll have a -2x and another -2x. So that'll be x times x. I'll have a -2 here, a -2 here. What I need to complete my square is a 4. So I'll add 4 to both sides. So x minus 2 squared on the left equals -1 plus 4 is 3 on the right. Now using the square root property, x minus 2 is either the positive or the negative square root of 3. Adding 2 to both sides, x is 2 plus or minus root 3. So my zeros are 2 plus root 3 and 2 minus root 3. And so my factors are x minus 2 plus root 3 and x minus 2 minus root 3. Okay, I think we're done now, right? We've broken everything down into linear factors. Let's go back and find them all. So here are two real roots and the corresponding linear factors. Here's another real root and the corresponding linear factor. And of course, at the very beginning, we have the irreducible quadratic factor that we were given. So this polynomial factors fully as originally we had x to the fifth minus 14x to the third minus 26x squared plus 105x minus 26. And now we know that that factors as x squared plus 6x plus 13, the irreducible quadratic we were given, times x minus 2 times x minus 2 plus root 3 times x minus 2 minus root 3. And so this was given. This was a rational root that we found through trial and error. And then these two we found by completing the square. So this is the fully factored form, and the real roots are 2, 2 plus root 3, and 2 minus root 3. Again, we found 2 through trial and error, and then we found the last 2 by completing the square. And this is what it'll typically look like when we fully factor something. We'll sometimes start given one or more factors. We'll divide by the factors we're given, and then we'll use the rational roots theorem and trial and error to pull out roots until we're down to something quadratic. And then we'll use our techniques for quadratics at the end. Strictly speaking, this won't work for every polynomial. We might have a polynomial with, say, 4 irrational roots. We might have a polynomial that's just the product of all irreducible quadratics. But it will work for many polynomials. It'll work for a lot of the kind of polynomials we want to find roots for in practice. And when the numbers get unpleasant, we can use numerical techniques to approximate this process and get at least decimal approximations for the real zeros and the factors. But this process is what underlies it. So we want to understand this process first.